Disney has long been known for making some of the highest quality animated movies of all time. Their immaculate attention to detail awes audiences worldwide. What most people don't realize, though, is that animating every single fabric stitch, hair strand, and tree leaf throughout an entire movie is virtually impossible. Unless, of course, you know a bit of magic. And by magic, I mean calculus. Today I am going to show you how to use calculus to animate a strand of grass from Pixar's Brave. This sounds mundane, but it's actually vital to the movie, as believable worlds are the first step to engaging audiences in a fantasy realm. Though grass does resemble a parabola, the ambiguity of nature means we don't have a set equation for the curve. Calculus comes in handy because it allows us to quickly and effectively create any curve we want. Some artists are familiar with the string art construction method, where you continuously take the midpoint of the midpoint of the midpoint of the midpoint. Yeah, I think you get the point. But seriously, who has time for that? Exactly. Instead, we can look to more advanced calculus, like parametric equations. Parametric equations are a set of equations with which you can find the coordinates of any point on any curve. These equations are functions of a new unknown variable, usually t, called the parameter. The setup of these equations is known as parametrization and involves defining x and y as a function of this third variable, t. Without an equation for the curve, we must use weighted averages. Essentially, weighted averages serve as generalized representations that allow you to compute any point on a line segment. In the case on the screen, we've randomly placed point M and divided the segment into t, and for what's remaining, 1 minus t. The formula that results is m equals 1 minus ta plus tb. Through a collection of line segments, we can work our way to the parabola. First, we define x and y as the weighted averages of the two legs of our control polygon. By the way, control polygons are what animators use to outline the general framework of their parabolic arcs. We can easily determine the location of point P and R this way. These known functions give us the values needed for a brand new tangent line, where point P, the coordinate of the parabola, lies. As values of t change, point P will shift location. If we plot point P a few times, we will see a curve begin to form. The parametric equations of function Q and function R give us the values needed for P's coordinates. Think of P as being no different than y equals x squared. Both are equations for finding points on a parabola. Parametric equations are very computer-friendly. All Disney animators have to do is find their set of parametric equations and type them into the computer. What you're looking at right now is my own handiwork for finding a random point P on the curve. Of course, what I've done by hand for one value of t, the computer does for all values of t faster than we can blink our eyes. Nevertheless, it's important to understand how the math is happening so we are mindful and educated. Now I'm sure you're curious to see how this looks in action. Here's a clip of me working in Khan Academy. This is a simplified version of Disney software. The computer uses our parametric equations to instantaneously compute the points for the entire curve. This happens seamlessly for every frame variation. When I play back the recording, the motion lapses the animation. Animators are so lucky to have calculus in their lives to improve the practicality, efficiency, and accuracy of their work. I really enjoyed this opportunity to learn something new, but I understand the limitations of this knowledge in my daily life. So before I leave you, I want to show you how these same principles can be applied to visual art. Let's take the chair from my most recent painting. Again, this is real life, so we don't have an equation given to us on a silver platter. Fortunately, in calculus we can use tangent lines to sculpt the form of a curve. I decided to find the average slope for a few tangent lines and justify their equivalency to the instant slope of the curve with the mean value theorem. But before we get ahead of ourselves, let's understand how I'm getting coordinates in the first place. First, I would grid my canvas as if it were the fourth quadrant. Positive x, negative y, origin in the top left corner. Then I could use the reference photo to get the exact slope of the curve and transfer those slopes over to my canvas. With enough tangent lines, my curve could be molded. Though my painting is complete, the visual models show what a useful tool calculus could have been in eliminating error. Since my goal with my paintings is to be as realistic as possible, calculus sure would have been my ally in this past work and will definitely be a part of my art in the future. I hope you've enjoyed learning how calculus applies to the many realms of art. These two seemingly polar opposites actually complement each other to ensure the highest quality work.